Today we want to talk about semiconductors, and particularly about the things that govern the engineering relevance of semiconductors, which is semiconductor junctions between extrinsic semiconductors. Remember that there are two kinds of semiconductors: intrinsic semiconductors, in which the conductivity is simply governed by the band gap and the difficulty of exciting electrons across it, and then extrinsic semiconductors, where the conductivity and the type of conduction are governed by the kinds of dopants or impurities or solvents that put in. The classic examples, and in fact the most widely used dopants, of silicon, are phosphorus, which produces extra electrons and therefore creates isolated sites which are just below the conduction band of the semiconductor. At temperature zero, these donor sites are all filled with electrons, but they're only slightly below the conduction band, so these electrons can be excited and become conductors relatively easily at low temperature. So we get a conductivity that is governed by the number of donor sites and a type of conduction that is dominated by electrons. These are called N-type semiconductors. The alternative of P-type semiconductors, for example, using boron as a dopant of silicon, boron has valence 3, so it's missing an electron. That creates an array of empty sites just above the valence band. At T equals 0, these sites are all unoccupied. However, they can accept electrons from the valence band, leaving holes behind. So in a P-type semiconductor, in which we use acceptors, the conductivity is controlled by the number of acceptor atoms, and the types of the conduction is due to the motion of holes through the valence band. So by controlling the dopant that we use, we can control the conductivity of the semiconductor, and more importantly, we control the type of carrier that is giving that conductivity. Electrons in the case of N-type semiconductors, holes in the case of P-type semiconductors. Well, as I mentioned last time, if we simply plot the current carrying density, the carrier density of a extrinsic semiconductor as a function of 1 over T, we get curves that tend to look like this for typical choices of active impurity densities. At high temperature, the intrinsic excitation processes dominate, and all semiconductors behave as intrinsic semiconductors. At very low temperature, the donor or acceptor sites dominate, and the semiconductors behave as extrinsic semiconductors, with the carrier increasing, the logarithm of the carrier density increasing with 1 over T, with the slope, in this case, donor electron excitation energy divided by 2 T. In a well-designed semiconductor, there is an intermediate region here where the semiconductor is saturated. That is, the donors or acceptors, the active sites, are essentially all used, and the extrinsic excitation processes are not important. So we get a range of temperatures over which the carrier density is approximately constant. Since the carrier density is approximately constant, the semiconductor behavior is not that strong a function of temperature, and this is a good region in which to design electronic devices. Let me caution you that what I have plotted here is the carrier density given by these equations, rather than the conductivity. The conductivity sigma is the carrier density multiplied by the charge multiplied by the mobility. In fact, if you look at the conductivity in the saturated region, you'll find that it goes down slightly as the temperature goes up. And the reason is the mobility, the resistivity of the material. For a fixed carrier density, the resistivity increases as the temperature goes up because the photons scatter. So in the saturated region, it's repaid by the metal phase. The carrier density is rather sensitive to temperature, the mobility goes down as the temperature goes up. So in this region, as the temperature goes up, the conductivity will actually increase. One of the things we have to be concerned about in extrinsic semiconductors is the problem of degeneracy. As we increase the, for example, donor density in this example, the conductivity increases at all temperatures in which extrinsic behavior dominates. So you might say, well, great, we can create a wonderful semiconductor with very high conductivity by just increasing the carrier density. The problem with doing that is that it is critical to the properties of extrinsic semiconductors that the carrier levels be independent of one another so that they can behave independently. If we start getting the impurity density or the solute density too high, then these sites will see one another, essentially the orbitals, so the extra electrons around the donor atoms will begin to roll out. When that becomes the case, then the material begins to behave as a metal, because we begin to develop a continuous band space here in the donor level. This is called the donor band, and it essentially causes the semiconductor to cease to be a semiconductor and begin to behave like a metal, because the donor band is only partly filled, and the donor electrons present only material filled. This is a problem. In fact, this is the problem. I told you quite some time ago that the enabling technology for the microelectronics industry was the discovery of zone node, a very simple, economical way to make very pure materials. Why was that so critical? Well, this is the reason it's so critical. Unless we have very pure materials to start with, we can't create a material in which the electrically active sites, donors or acceptors, behave independently. If the material is degenerate, it behaves like a metal. And adding donors or acceptors to something that's already degenerate is not a way to get null. So before we could make good semiconductors, it was absolutely essential to create very, very pure crystals so that low concentrations of donors or acceptors would behave, and they would behave as we expect extrinsic semiconductors to behave. So that was the issue. In fact, you can also use degeneracy. Suppose you're making a device and you have an extrinsic semiconductor over here, and you have an extrinsic semiconductor over here, and you would like to create a region that conducts metallic connected to it. One way to do this is to overdose the intermediate region. If you don't the intermediate region enough, it becomes degenerate, and it behaves like a metal. And this is one way of connecting two semiconductors in different regions of the chip. So the conductor region is different. There are, of course, other ways of doing that, but that is titration. There ain't no such thing as a completely pure material. Given the second law, every semiconductor, no matter how carefully you try to purify it, if you're taking a body of reasonable size, it not only has impurities in it, it has a whole periodic table, always. If the material has been purified, that doesn't mean that it doesn't have impurities. It means that the level of impurities, the concentration of impurities, has been reduced to a very low value, but they're still there. For example, if we want to make an N-type conductor with donors, we have to accept the fact that within that material there are going to be some impurities that act as acceptors and produce impurity levels within the material that lie below the donor level that we're going to use. So the first thing that will happen when you start adding donor elements to the semiconductor is that the electrons at the donor level will drop down and fill the acceptor levels that are within the band gap below. So you never get complete efficiency out of the donors that you add. The first set of donors are used to titrate or neutralize the acceptor impurities that are available within the material. This, of course, just reinforces the idea that you need a high purity starting material to minimize the number of these acceptor impurities. Because if you have too many of these acceptor impurities, you can't get extended behavior at all without increasing the number of donors so high that you make it degenerate. this is kind of a limit on what good semiconductors can be. Junctions. Extrinsic semiconductors are useful not because they're great conductors, but because they make great junctions. Now, what do I mean by that? We can join N-type and P-type regions to create a junction which has asymmetric electrical properties that are very useful to talk about today. But note that that can be done by just doping adjacent regions. The way we tend to make semiconductor devices is we take a single sheet or die of semiconductor, of this silicon in the usual case, and we dope regions to that silicon. If we dope one region with boron, that region will be N-type. If we dope an immediately adjacent region with phosphorus, that region, phosphorus will be N-type, boron will be P-type. If they're right next to each other, the boundary between them will be junction. Yes. But you see, any donor level that has an energy higher than the donor level I'm putting in will not affect it because the donor levels are filled. Any donor levels that are slightly below this won't affect it either because those donor levels are filled. The only things that can affect this are any empty levels, no matter what their energy may be, that have lower energies than the donor I'm putting in. Because those empty levels will be filled by the semiconductor can lower its energy by moving electrons from the donor levels to the empty. So the only ones you have to care about are empty levels or acceptor levels, if you want, whose energies are below the donor. These may be true acceptors down here in the valence band, or they may be states way out here in the middle of the band gap. It doesn't matter. So long as they're empty and have energies lower than this, then they have to be counted. Well, you're not going to get donor behavior, N-type behavior, until you've canceled out all of these things. Now, if you just naturally had donors in the material, those donors will cancel out these acceptors for you. So there's certain balancing acts just from the impurity that naturally takes. But if you have an excess of acceptor impurity, you have to titrate those before you can empty them. Yeah, so that's what I'm trying to see, man. It's like, oh, typically, shouldn't they already cancel each other out? Well, you know, if you're really lucky, they would. But lucky is not something you can do. In order to get controls on the behavior, you have to do it. I don't know. Yeah, you just have to change that. Is this working? Okay, is that better? Okay, good. As you can see, I'm not an electrical engineer. Yeah, the ideal situation, of course, would be a perfectly pure material. You wouldn't have to worry about this. In the real world, you would. And since, if you don't get real purity in your starting material, you can have all kinds of junk here in the band gap. That junk has to be accounted for before you get good properties, and it becomes very difficult to make a really controllable semiconductor. So the zone melting was the breakthrough that got you to very pure materials and let you control this kind of behavior. You still have to worry about it a little bit, but not like you do if you can't control the purity of your materials. Okay, let's talk about junctions now. What happens at an NP junction? What happens at an NP junction is really pretty straightforward. Remember that, first of all, let's focus not on the donor and acceptor levels, but on the Fermi level. At low temperature in a donor material, the Fermi level is going to wind up halfway between the donor levels and the bottom of the conduction band. It's proven mathematically in the notes. I won't bore you with mathematics. But at low temperature, the Fermi level is going to be halfway in between the donor level and the bottom of the conduction band. In an acceptor material, the Fermi level is going to be halfway between the top of the valence band and the acceptor level. So if we put those two together, and we imagine doing that, and they have an impermeable membrane between them at time zero, so there's no electrical contact, then at time zero, the Fermi level on the donor side would be up here at the top of the band gap. The Fermi level on the acceptor side would be down here at the bottom of the band gap. So what happens when we break this imaginary membrane and let these two devices start communicating with one another? Well, you're trying to lower the energy. So what's going to happen is immediately electrons will flow from the N side into the P side. And those electrons will start annihilating these holes on the P side. But as soon as that process starts, you start building up an excess negative charge on the P side and an excess positive charge on the N side. And that will cause the electron levels on the N side to go down and the electron levels on the P side to come up. And that process will continue until we finally get into a situation where the Fermi level is constant all the way through the junction. Because once the Fermi level is constant, there's no longer a driving force for any electron motion. The electrons can no longer decrease their energy by moving from one place to another. So what quickly happens in a junction is that the bands on the N side are displaced downward, the bands on the P side are displaced upward, and that continues until the Fermi level is constant through the junction, as you can see there. Well, that behavior, incidentally, when that happens, the currents that flow through the material are the same on both sides. Remember that, according to Fermi-Dirac statistics, the probability that a given electron level is occupied is simply proportional to the exponent of its distance from the Fermi level. The least energetic electron that can flow from the N side to the P side, after the situation maintains, has an energy just equal to the bottom of the conduction band over here on the P side. That energy is, of course, the same distance above the Fermi level on both the N side and the P side. So the current flowing from N to P is identical from the leakage current flowing N to P is identical to the leakage current flowing from P to N as soon as this equilibrium is maintained and the Fermi level is the same through the interface. The same is true of the hole current down here. The probability that a hole exists at an energy level just equal to the top of the valence band on the N side is the same in both the N and the P regions. Therefore, the leakage current of holes is the same in both directions. So as soon as we reach this equilibration where the Fermi level is the same through the interface, then electrons and holes are still moving, but they're moving at the same rate across the interface and there's no net flow anymore. However, what now happens as a consequence of this band bias across the interface is that we've now created something that has very asymmetric conductive properties. Now understand why that's true. Suppose we place electrodes, negative electrode over here, positive electrode over here, to put this joint in what we call a positive bias. if I place a negative potential on the inside, that will raise the energy of the electrons on the inside. That will raise the population of electrons up here, the population of electrons that can move from the inside to the p side. If if V is the potential I put on, EV is the increase in energy here on the inside. For reasons that have to do with electron mobility, this potential drop will very quickly, ordinarily, be concentrated right there at the interface. So we get a step in the potential there at the interface, and the electrons on the inside of the interface, the electron population here at the bottom of the conduction band, where electrons can move from one side to the other, that increases by exponent EV over KT. So we suddenly get a big increase in the electron density on the inside. Those electrons move, and as a consequence, we get a current, a net current from the inside to the p side, and that current increases exponentially as the applied voltage. There, of course, is an equal and opposite current of holes from the p side to the inside for the same reason, and therefore, if we put the junction in forward bias, put a negative terminal over here, negative potential, a positive terminal over here, electrons flow from the end to the p side, electrons are introduced into the material from the negative terminal to keep the current going, and we get a current flow. This is what we call forward bias. This material behaves just like a metallic conductor would. In fact, it obeys Ohm's law when the potential is small, because if you just expand the exponent, you'll find that the net current, forward minus reverse current, is simply proportional to the applied voltage. So with this arrangement of electrodes, our junction is in forward bias. But now let's reverse that. And, well, actually, this is still forward bias. See what happens if we do that. The net flux of electrons is the electrons in the positive direction plus the electron flow in the negative direction. The electron flow in the negative direction is just equal to the electron content at that level. So our net current is the current of electrons, which is just the population of the original population of states up here at the bottom of the electron band, times the exponent of EV over KT minus 1, where the minus 1 accounts for the reverse current. Now, this equation holds whether I have the voltage is positive or negative. If the voltage I placed is positive, then the positive current increases dramatically as the voltage is raised. And I get a behavior that looks something like this. Increase the voltage, the current goes up quite dramatically. But now let the voltage be negative, so we bias in the other direction. Essentially, we're putting a negative terminal over here and a positive terminal over there. If we bias in the negative direction, then voltage is negative. Exponent minus EV over KT goes quickly to 0. So the biggest current we can get in the reverse direction with reverse bias is just the leakage current, JE0, that we had in the first place. So the net current voltage characteristic looks like this. If we put the junction in forward bias, the number of electrons that can move forward increases exponentially as we increase EV. If we put the junction in negative bias, that means EV is negative, that means we drop the Fermi level on the inside. The high density of electrons is on the p side, but that density of electrons is fixed by the difference between the Fermi level and the bottom of the conduction band on the p side, and that is simply equal to the leakage current that was there before we imposed the voltage. So very, very quickly in reverse bias, the current damps out at a very small value. To all intents and purposes, forward bias, this is a conductor. Reverse bias, for all intents and purposes, it doesn't conduct at all. There's a small leakage current, but we can usually ignore that. So this is a one-sided conductor, an asymmetric conductor. Put it in forward bias, electrons charge forward. Put it in negative bias, the electrons don't move at all. Well, tiny bit, but essentially not at all. So we have a device which is a asymmetric conductor. In forward bias, the majority carriers diffuse across the interface. They become minority carriers over here. They're immediately destroyed by recombination. And the majority carrier density determines the current and it's replenished by injection. You want to see what's happening here. These electrons have at the bottom of the conduction band, are capable of moving forward. They move forward. As soon as they get to this side of the junction, they encounter a high density of holes, and they are therefore annihilated. So the electrons come over here, meet the density of holes, and they're annihilated right here at the interface. In order to conclude this process, we have a terminal at the far end, and electrons are constantly being introduced from that terminal as part of the circuit. There would be a complete circuit here. Similarly, there's a positive terminal over here on the right-hand side, and holes are constantly being introduced from that right-hand circuit terminal. So we have electrons, holes, meeting at the interface, recombining, destroying each other. New electrons and holes are constantly coming in. The net effect is a continuous current through the system in forward bias. Now let's go to reverse bias. If we go to reverse bias, the electrons are flowing out to this positive terminal. That means that electrons are getting depleted here at the interface. There are no electrons. What electrons can come in to replace them? The only electrons that can come in to replace them are the electrons that are over here on the p side. And that electron density is very low because you're well above the Fermi level here at the bottom of the conduction band. So this high population of electrons is swept out. The only electrons that can replenish them are this very low population of electrons on this side. The holes over here are also being swept out. The only way the holes can be replenished is the low population of holes on the inside. So we get a very small, steady current when we have this sample in reverse bias. To a certain extent, the current is determined by the rate at which we can create new carriers by activation from the conduction to the valence of the conduction band. So we have a one-sided behavior. Easy flow of current in forward bias, poor flow of current in reverse bias. It's a one-sided conductor. Well, how can we use that? We can use it in a number of different ways. Actually, one way to use it is suppose we want to take alternating current and turn it into direct current. Alternating current, we flow the current one direction, the other way, one way, the other way, and so on. Suppose you try to introduce an alternating